Hey Morton, I think you're muted on the Zoom. No one can hear you if you're talking right now.
I don't see a mute icon for him.
Yeah. So I think his headset's messed up. Hmm. Yeah, hold on. I don't think you can hear us either. Yeah, I think he's trying to fix it.
Here. And let's now go back to the whiteboard and try to wrap up this discussion about variational calculus, and in particular the case where we have a equations with a constraint. So what we looked at on Friday was a specific example. So let's bring this up again. So this is variational calculus with constraints. Constraints and Euler-Lagrange and Lagrangians. Constraints and Lagrangians. So what we have looked at is a Lagrangian, which in one dimension was something which we defined to be a function of position, velocity, and time. We can generalize this to a general variable, which, and you've probably seen this in a textbook, so this would be a vector of q, a vector of the velocity of q, so this will be a general velocity. And in principle, we can actually have this q to be represented by many variables. So we would not be limited to, let's say, x, y, and z, but we could have a q1, q2, q3, etc., up to a q of n. And the case which we looked at on Wednesday last week was the system in polar coordinates, when we made a transformation from Cartesian coordinates to polar coordinates. So that was a typical example where we then had an L of x, of v of x, and then we had y, v of y, and t, and we transformed that one into something which depended on the radius or the distance, the absolute value of the distance, and then we had the radial velocity, we had an angle phi, and then we had the angular velocity and time in addition. So these q's, as you see, they can be represented by many different types of variables. And we normally call this generalized coordinates and generalized velocities. And in general, what we have is a set of equations where we then have a dl derivative with respect to one of these q's. And these are the set of equations which we have to set up in order to find the equations of motion for one specific variable. And this will be given by the partial derivative of this q of I, and that's the derivative. And these are the so-called Euler-Lagrange equations, which we derived last week. Now, let me just quickly repeat some of these things. Now, one of the things which we looked at last week was a case where we had constraints. And one type of constraint is something which is called a holomonic constraint. Holomonic. And this means that what we have is a function of g, which is a function of these variables, q1, q2, q3, up to some q of n, being equal to 0. Now, what we did on Friday was to look at the equations which led to the motion along an incline. So we had an angle alpha here, and then we had an object which was falling down here, or sliding down, which is better. And then we had the gravitational force acting here, Fg. We had y, the y direction, and then we had x here. And then we had a constraint where our specific function of x and y was now given by y minus x times tan alpha, and this is equal to 0. So this is an example of that type of equations which we have. Now, when we solved these equations, that is, we actually plugged in the Euler-Lagrange equations, what we found then, and there was a small typo in the exercise from last week, of what we did on Friday. So we should actually have a plus. We got a plus lambda of tan alpha squared plus lambda minus mg equal to 0. And that led to a set of equations where we found that this parameter lambda was now given by mg of cosine squared alpha. And then we had the equations of motion in the x direction, where we had a minus g, so this is the acceleration in the x direction, times a sine alpha times a cosine alpha. And then we had the equation of motion in the y direction, which was simply a minus g times sine alpha squared. And this function lambda comes, or this variable lambda, comes actually from the Lagrangian here, which is now given in terms of v of x, of y, v of y, of t, which was equal to the kinetic energy. So we have the velocity in the x direction plus the velocity in the y direction. And then we had the potential energy, which in our case was minus m times g times y, plus the specific function g of x or y, which in our case is equal to y minus x times tan alpha. Now, what we are going to discuss a little bit more in detail now is how can we introduce such a function with this variable lambda. So this variable lambda is called a Lagrange multiplier. And it reflects the fact that x and y are no longer independent variables. So let's look at a case now, which is a little bit disconnected from the physics. So let's take a plain mathematics example. and see if we can use that one to motivate the introduction of these Lagrangian multipliers, that is this parameter lambda. So there's going to be one such parameter for every variable which is no longer independent. So if we have no constraint on the problem, then x and y can take any value. But as soon as we have a constraint here, that is, the object is moving on the incline, then there is a limit on which values one of these can take. So let's look at a perhaps a little bit more familiar case, which you've seen in perhaps in mathematics courses. So let's take another example. So let's assume that we have a function which we want to minimize. And this function is just a given function, which I just cooked up one of these days. So nothing exciting. And the function is going to be given by, so we have a, let me just see, find my proper notes here. So I'm going to look at a case where I have a, so where did I put my function actually? Suddenly I just need to find back my function here. So this is the day when nothing functions anymore. Like, where did I put that one? I had it written down somewhere. Let me just see here. So this is my lucky day, eh? Here we go. So we have a function which we want to minimize. So we want to minimize. So this is a function f of x1 and x2, and it's given by minus 3x1 minus 6 of x1 times x2, and then it's minus 5 of x2 squared plus 7x1 plus 5 times x2. So if x1 and x2 are free variables, we can do whatever we want with them, but they can take any value. And if we want to minimize it, we would typically take the derivative, and we will set the derivative of this function with respect to x1 and x2 equal to 0. And then we would find the minimum of this function. But we cannot put a constraint. And the constraint we could put on the function is that we would have something like this, but subject to, so let's say we put a subject to x1 plus x2 is equal to 5. So that means that when you're looking after the solution here, what you have is something like this. So if you put x1 on that axis and x2 here, so we have 1, 2, 3, 4, 5, and then we know that this is a line. So we're actually looking after the solution which lies on this line here for the function f, which is a function of x1 and x2. Now we know how to solve this one. This is something which is pretty straightforward, because we would now, when we do this, without thinking of variational calculus, we would simply now replace x2 with x1. So that means that x2 must be equal to x1 minus 5. Sorry, not minus 5, but 5 minus x1. And then we would simply plug that in to the function. So that means that f of x1 and x2 becomes now a new function, which is a function of just x1. So we would simply put that in, and then we would get minus 3 times x1 squared minus 6x1, 5 minus x1, and then we get minus 5 minus x1 squared plus 7x1 plus 5 times 5 minus x1. And if I bring all these expressions together, I should get 2 minus x1 squared plus 22 times x1 minus, and this should be minus 100 here. And then I want to find the optimal value. And, or rather the value at the minimum. So I would simply take and calculate the derivative of h with respect to x1, and I want that one equal to be 0. So that simply says that I have minus 4 times x1 plus 22, and that leads to x1 being equal to 11 divided by 2, and that leads again to x2 being equal to minus 1/2. So this will be a pretty straightforward way of solving it, right? So I guess I hope I didn't offend you with this kind of mathematics. So what we're going to do next is actually to rephrase this in terms of a Lagrangian with a constraint. So we are now going to define a new function and a new Lagrangian. So we can define a Lagrangian which looks like as follows. So Lagrangian with constraint. On Friday, we just took a top-down approach to this. And today we are going to try to bring in some more mathematics here. So we can now define, for this specific case, we can define a Lagrangian, which depends on x1, x2, and a parameter lambda, which is now simply this function, which is x1, x2, the function we started with, plus a lambda times g, and this function of g depends on x1 and x2, and we have defined this function to be a so-called holomonic function, and that's equal to x1 plus x2 minus 5 equal to 0. So that is the constraint which we have on x1 and x2. So it means that we want to optimize this problem with a constraint. So this technique, which you see here, is widely used in mathematics and in many mathematics type problems. So if you guys are going to study, let's say, machine learning, in many machine learning methods, you actually start with a function like this f, and then you may have some constraint that you want to parameterize your data to a specific range of values. And that means that one of the variables, or many of the variables, are no longer independent. So you cannot choose freely which one you want to use. And this is the case which happens when we have this motion with an incline. It's the same thing you will see with the mathematical pendulum, which we are coming back to at the end of this lecture. And then we are going to show how you can actually solve that exercise in homework number 9, which is exercise 5, how you can solve that with a constraint on the motion of the pendulum. So let's now use the Lagrangian formalism and extract the same solution which we found by just doing the plain mathematics which we would have done, right? So let's try to repeat this exercise. And it actually looks a little bit more complicated than just the simple, straightforward path which we took here, right? So we just made the substitutions, and then we took the derivative and found the optimal values. Now, what we're going to do now is instead to actually take and use the Lagrangian equations. So we're going to take the derivative of d dx1 minus d dt. There is no time here, by the way. And then you will also see that there is no derivative with respect to x1. And then we act on this with L, and we want this one to be 0. And when we take the derivative, what we get is minus 6 x1 minus 6 x2 plus 7 plus lambda is equal to 0. What happens next is that this gives me x1 plus x2, and that's equal to 1 divided by 6 of 7 plus lambda. And we know that this one, when you go back to the constraint which we had, this is actually equal to 5. That's the constraint which we put onto x1 plus x2. So this has to be equal to 5 when we use a constraint. And that leads to lambda equal to 23. So we found the optimal value for this parameter lambda. The next thing we're going to do now is simply to take the next derivative. So we have these generalized coordinates, which in our case are given by x2 and x1. And then I have the derivative with respect to x2 here. And there is no first derivative, and there is no time dependence. We want this one to be 0. And we do the math now. And what we get is that this is equal to minus 6 x1 minus 10 times x2 plus 5 plus lambda is equal to 0. And when we then plug in the value of lambda and do the calculations, and we have the two equations. So when we plug in, so we found an equation for lambda here. We know that x1 plus x2 is equal to 5. And then with the right value of lambda, which is equal to 23, we can then find x1, which is 11 divided by 2. So if you do the math, you will actually see that. And then we have x2 is equal to minus 1/2. So we actually got the same, the kind of same values, which we had in the previous case, but now we started with a function f with a specific constraint, and we use this principle of, or this mathematics of Lagrangian multipliers. So let me try to motivate a little bit this topic with Lagrangian multipliers and what that actually means. So let's now look at these parameters lambda, which we get. And let's stay with this simple function which we have. So what happens when we do this is that we are going to get variables which are no longer independent. And this can then be expressed in terms of a new function multiplied with a parameter. So let's look at our example. So what we want to is to minimize a general function. So we want to minimize. This is pretty common. And with the Lagrangian formalism, what we actually want to do is to minimize an integral over all the paths. So we want now to just minimize a general function, f of x1, x2, which is subject to a constraint. And this constraint is a constraint where we have this function g of x1 and x2 equal to 0. This constraint is then satisfied by a specific set of values. So it's satisfied by some x tilde equal to x1 tilde and x2 tilde. So what we're assuming now is that there is a set of x1 and x2s which satisfies this minimization problem with respect to a given constraint. Now, let's now try to demonstrate that this means that x1 and x2, one of these may not be an independent variable. So when we want to optimize this typical problem, what we would have then is a kind of necessary condition for d of f. So in the optimization here, what we want is a d of f, which is equal to 0. So when we look at the partial derivatives, so this will be a d of f partial derivative with respect to x1, dx1 plus a d of f and with respect to x2 of d of x2 equal to 0. So dx1 and dx2 are variations, and these points are actually, these are variations or points that are on the constraint. So let's take a look at that. So dx1 and dx2 are variations. Actually, in our case, they represent points that are on the constraint So we have set up the constraint, and then we know the values where the minimization or the optimization is satisfied is a x1 tilde. So we are now looking at a small variation around the values which give us the minimum or the optimization, and we assume that these two parameters, dx1 and dx2, they are assumed to be small. Now, if we assume that they are small, then we can Taylor expand this function g. So if we do the Taylor expansion, what we would get then is a g of x1 tilde plus dx1, and then we have an x2 tilde plus this dx2 here. And if we just stop at first order, then we get a g of x1 tilde, and this is actually the equations for where the constraints are satisfied, plus a dg of dx1 multiplied with dx1, plus a d of g of dx2 multiplied with dx2 here. So what we are going to assume now, since we are at the minimum, so we require that this function dg, which is now given by dg of dx1 plus dg of dx2, that this actually vanish. Sorry, this should be multiplied with dx2, should be equal to 0 at the point where we have optimized the problem, where x1 tilde and x2 tilde are those which give us the solutions. So we're going to make an assumption, and one of the assumptions we make is that this dg dx2 here is different from 0. So that's a plain assumption which we're going to make. And since we now have required that the terms you see here, that this dg is equal to 0, so since we have assumed that at the optimal set of optimal values, that means that this dx2, if I now take this equation which you see here, and simply use the fact that this has to be equal to 0, it means that dx2 must be equal to minus dg dx1 divided by dg, and we have made the assumption that this derivative with respect to x2 is not 0. So, and this is multiplied with dx1. And this must be satisfied by all values of dx1. So if I use that, then what we can show then is the following. I can show then that this d of f is then equal to, when I put this in again, into the equation for d of f, which we have up here, which we're also assuming at the minimum. So at the minimum itself, this function also has to be equal to 0, what the maximum or the optimal value. Then what we would get then is that we get d of f of dx1, and then we have minus, and then we have dg, derivative with respect to x1, divided by dg, derivative with respect to x2, multiplied with df of d, so this should be a partial derivative of dx2, and this is multiplied at the end with dx1. So it must be this must be satisfied for all values dx1. Satisfied by all possible values of dx1. So that means that what we would have then is the following. So I would have a d of f of dx1 of dg dx2. So I'm just multiplying out dg dx2 minus df dx2 dg dx1. And at the values of x1 tilde x2 tilde, this must be equal to 0. Then it's pretty common to define a parameter lambda, and you can define this parameter in terms of the function minus d of f, so there should be a d of f x2 here, df dx2 divided by, and this should also be a dx1 here. So if I define a parameter which I call df dx2 divided by dg dx2 here, so all dependence only on x2, then what I can rewrite is d of f equal to 0, and that's equal to a parameter d of f dx1 plus a parameter lambda multiplied with dg dx1. And this is equal to 0. And this parameter is normally called a Lagrangian multiplier. And that reflects the fact, Lagrange, let me just rewrite this properly. So this parameter lambda reflects simply the fact that one of the variables is no longer independent. So what I've done now is to rewrite this d of f in terms of the function, a function which now depends only on x1, one of the variables. So I've taken away the dependence on one of them. And what happens if you have more and more variables which are dependent, you can replace these with more and more of these parameters lambda. So the final story is that what you can do then is to replace your original function f with a function f plus a new function which is multiplied by this parameter lambda. So what you see here is a kind of mini motivation for why you get this variation, these so-called Lagrangian multipliers. So think of these as parameters which you add because you have a constraint on your equations, and any constraint you put on the equations brings in a dependency so that variables which previously were independent of each other, they are no longer independent. So one of them, in this case, two variables, one of them can be chosen freely, but the other one is then determined when you have fixed, let's say, x1. So the implications for us is that what we can do now, when we now go back to physics examples, is that we can now impose such a constraint. So this is relevant for the last homework now. If we now look at the physical pendulum, which we have seen before, so suppose now that we have this two-dimensional system. So we have the x-axis in this direction, and then we have the y-axis here. And in this case, it's going to be more convenient to express everything in terms of polar coordinates. So we have the pendulum here. It has a specific mass. We have the gravitational force here, F. There is a tension here, which acts on the rod here. Let's call this T. And some time ago, we actually derived these equations of motion. We have an angle phi. There is a distance now, and let's call this distance for r. So if we take the distance from the origin here, down here, so this distance is something which we will call for r. Now the pendulum, or this rod, or this object here has a length, L, and that's obviously given by the absolute value of r. Now what we are going to do now, instead of setting up the forces, which is something we did some time ago, before we began looking at the harmonic oscillations in proper, now we are going to use the Lagrangian formalism and simply derive the same equations of motions which we did before. Now, if you look at this object here, and now we want to impose a constraint. So we are going to go from Cartesian coordinates to polar coordinates, which is more convenient for this specific case. So we are going to go from x and y to r and phi, as we did in the problem with the two-body problems. So we would have a y, which is given by r times cosine phi, and x, which is given by r times sine of phi. And that simply follows from the way we have defined the coordinate system and the angles here. Now, if you now want to use the Lagrangian formalism, there's going to be a constraint here. So if you want to set up a mathematical expression for the constraint, what kind of condition would you put in here? If you look at this problem, what would the constraint be here on the variables? So you have phi and r. Is there a specific constraint on one of these variables? So if you look at the equations which we have here, or the system, not the equation, but the system. So, yeah?
Would it be L?
It will be L. So we would actually have a constraint if we assume that this rod doesn't change at all. So that means that R, the absolute value of the distance, has to be equal to L. So it means that the constraint which we would put up now is R equal to L. So we would put up a constraint which is simply R equal to L. And then we can now define a Lagrangian which is going to depend on R, the radial velocity as before. We have the angle phi, the angular velocity, we have time. This is going to be given by kinetic energy, which we already have seen how to transform to polar coordinates. So I'm just setting up the expression here for you, because we did this some time ago. So this is given by r radial velocity squared plus radius squared times angular velocity squared. Then in addition, what we have is a gravitational potential. So we have mg, and then we have r. And since we defined y to be r times cosine phi, this has to be equal to r times cosine phi. But then we have a constraint. And the constraint simply says that we must have this Lagrangian multiplier, which is given by r minus L, because we require that r minus L is equal to 0. So this function with a constraint depends only on one of the variables. So this is the way we are going to proceed now and derive the equations of motion, where we have kinetic and potential energy plus a constraint. So if there was no constraint on the motion, you would only have kinetic and potential energy. And it could then be a little bit more difficult to actually extract the equations of motions in case there is a constraint which is difficult to model. So let's do the mathematics now with the Euler-Lagrange formalism. So what we are going to do now is simply to take the derivative with respect to r. So we take the Euler-Lagrange equations, minus d dt of d of r dot. And we require that that one has to be equal to 0. So if we do the mathematics, what we get then is that d dr of L is equal to m times r of phi dot squared. So that's the first term, because we have an r dependence here, but we have an r dependence here, and we also have an r dependence there. So what we get then is plus m times g times cosine phi plus lambda. And then we take the next term, which is a d of L of d of r, and that is simply equal to m times r when we go back to the Lagrangian. So what we would get then is that when we take the derivative here, we get a factor of 2 and m times r. And that means that when we take the second derivative, so that means that when we now take the second derivative, no, not the second derivative, but the derivative respect to t, then we have m of r, and this is simply m times r second derivative. So if I collect all terms now, if we do that, what we are going to get is m times r dot, and that's equal to m times r of phi dot squared plus m times g of cosine phi plus lambda. So that doesn't look so exciting, and we have not seen this equation. It's not so easy to translate into what we've seen before. But let's see what happens with the angular equations. So if we now take the angles, so we're going to need dl d phi, and that's given by, when we now look at the equations here, what we are going to get is an equation which now contains the m times g, so we take the derivatives with cosine, with respect to cosine. So that gives us a minus sine of phi, and then we have an mg times r. So that specific derivative is going to be equal to minus mg of r of sine of phi. And then we can take the derivative with respect to time. So then we will get a d of l of d phi dot. So if we go back to the Lagrangian, which we have, we see now that what we have is a dependence on phi dot, which comes in here. And that's the only place where we have it. So that's going to be given by m times r squared multiplied with a phi dot. Now, if I then plug it into the equations, what I get now is simply m times r squared of phi dot is equal to minus m times g of r of sine phi. So we can get rid of the m's here. We get rid of one of the r's like this. So what we get then is phi dot equal to minus g divided by r times sine of phi. And we know that r is actually equal to L. So this is given by minus g divided by L of sine of phi. And this is the same as minus omega squared multiplied with sine of phi, where omega squared is simply given by g over L, which is what we had in, I think it was homework number 7 or 8, when we did the mathematical pendulum. And this was the equation which we would solve for the angle phi. Now, if you now go back to the equation for the radial velocity, so this equation which you see here is the one which we have been solving before. So if you take this equation, this is the one which we had when we were looking at a pendulum without any form for damping or any form for external applied force. Now, if you now go back to the equations which you have for the radial velocity and the radial acceleration here, if you look at the left-hand side here, can you say something about the left-hand side here? What kind of, yeah?
Just that that's the force.
With the airports here, I have some hearing problem. But the if you think of the fact that R is equal to L, would R change with time if you look at the equation? So it means that's equal to 0. So in that specific case, what we can do now is to fix the value of lambda in terms of the derivative of phi and the angle phi. So what it means then, if we now look at this equation which we have here, this specific one, since r, this is the radial acceleration, and r is a constant, it's equal to L, we have imposed that that one cannot change with time. So it means that the radial acceleration has to be equal to 0. So what it means then is that we would have 0 is equal to m times r of phi dot squared plus m times g times cosine phi plus this lambda. And that means that lambda is now going simply to be equal to minus m times r of phi dot minus m times g of cosine phi. Now r is fixed. So as soon as we find, as soon as we solve the equations when solving, and this is essentially what you did in one of the homeworks, when you solve the differential equation for phi dot equal to minus omega squared times sine of phi, then what we get then, we find phi and the angular velocity, right? So when we have the angular velocity and the angle itself as a function of time, then we know the value for this parameter lambda. Now, what does this parameter lambda actually express for us? So if you think back to what we did on Friday, we found that lambda meant something.
So if you look at this parameter lambda, what does that one actually represent for us?
It's an external force.
That's the force. So
that actually represents the force. And in our case, if we go back to the equations here, so the only thing we need to solve when we solve differential equations is actually this equation which you see here. However, that gives us the parameter lambda, which now is going to be interpreted as this force which you see here, which is acting on the pendulum. So we know the gravitational force, but now we get an expression for this force T, which is a function of this parameter, which is given by this parameter lambda. So that's going to be the additional component, which we now can actually define by using this Lagrangian formalism with a constraint. And that's extremely powerful. So we don't need to set up the equation for this specific force. We can actually derive it from the Lagrangian formalism with a specific constraint. And then the expression for that force comes out when we solve the angular equations. Then we have the angular velocity and the angle itself, and we can plug that back in and determine this parameter lambda, which would depend on the time evolution of the angular velocity and the time evolution of the angle. Because that force will also change as a function of time, right? Okay, I see our time is over, so I'm going to stop the recording now. Feel free to hang around. I see that there's some people who want to come in here and use the room. I'm just going to, for those of you online, I'm just going to stop the recording, but feel free to